Alright, good afternoon. Today we are gonna continue on Mohr circle. So if you have time, we go through the three-dimensional Mohr circle as well. Also we will look at the mechanical design toolbox and the math lab that you may need to solve some of the homework problem with that toolbox. So
I was going to say, that will go across the line.
Just to clarify. Make sure we got that straight. Okay, that's it.
since I'm going to use this table, I just rewrote it again. If you are given with a plane stress element like this, and I ask you to find the principal direction with using the transformation equation, you can use Vp over there and corresponding principal normal stresses. The Mohr circle is gonna do the same thing, but it's a graphical approach. So basically, it's not. It's just a different method to visualize this equation. What you need to do when you are given with a stress element like this, you pick a point in this plane, just label this as A, and one point on this plane, and label this as B. And then try to write the coordinates of point A and point B, such that the Mohr convention is tensile stress is positive, compressive is negative for normal. And for shear stress, if it's making clockwise, you should consider positive, and if it's making counterclockwise rotation, we consider that as a negative. As I said, in entire of this course, counterclockwise is always positive, except on the Mohr circle. So Mohr circle, we just look at the shear stress. If it makes a counterclockwise, we look at it as a negative sign. So this sigma x it's a tensile, so it's going to be positive sigma x. But this tau xy is going to rotate this square in counterclockwise direction, and counterclockwise is going to be negative. So negative tau xy. For point B, the normal stress is sigma y, but the shear stress applied to this plane is making clockwise rotation, and clockwise is positive, so positive tau xy. Mohr circle has two axes. Axis x is representing normal stress and axis y is representing shear stress. Just locate point A and B. I assume that sigma x is greater than sigma y. Since I would like to locate the point, I should have this assumption. So if this is sigma x, for example, this is tau xy, negative of that is going to be right here. So sigma x and negative tau xy, it's going to give me this point. Point A. Sigma y, point B is gonna have a positive sigma y and positive tau xy, so I should locate it. For example, if this is sigma y, this is positive tau xy, I can locate point B somewhere here. Then if I connect these two, I will get line AB. So the center of this point has the coordinates of sigma x plus sigma y divided by 2 and 0. Which is going to be this point. And the radius or the half length of AB is going to be AB divided by 2. Is going to be half of sigma x minus sigma y divided by 2 squared tau xy minus tau xy squared. And if I bring this half inside the square, it's going to be 4. So s square root of sigma x minus sigma y squared divided by 4 plus tau xy squared. 4 divided by 4 is going to be 1. And if I move this 4 inside the square, it's going to be 2. So it's going to be sigma x minus sigma y divided by 2 squared plus tau xy squared. I label this as a radius of a circle. So I'm going to draw a circle with this center and this radius. So it's going to look like this. Line AB is representing the stress element at this plane. So if I want to know what would be the stress element if I rotate it by the angle of phi. So if I change the angle of plane, I pick a new plane. I would like to know what would be the sigma phi and shear stress applied to this, and what would be the shear stress and the normal stress applied to this plane. Basically, what would be the normal stress and shear stress applied to point A, which is located on this plane, and point B, which is located on this plane. What I need to do on the Mohr circle, I just need to rotate this line by the angle of 2 phi. So whatever is the angle here, multiplied by 2, and rotate that line by the angle of 2 phi. So I rotate it in counterclockwise, so I should rotate this in counterclockwise direction. So if this is 2 feet, point A is gonna end up to the new location, and point B is gonna be at the new location. Then what I need to do, I just need to read this number, and this number is gonna be the sigma phi at point A, and if I read this number, it's gonna be the shear stress at this plane. Similarly for point B, whatever is the normal stress or coordinates of point B in the x-axis is representing sigma phi b and shear stress at point B. Is that clear? How the Mohr circle is working? Any question before I move on? All right. Now, if I ask you what would be the principal normal stress and principal direction for this state of stress element, what you can do with the plane stress transformation equation, you can plug in the numbers and find phi p and sigma prime 1 and 2. But here, how can we do that? If you look at the plane in this circle, if I rotate this line in counterclockwise in this direction, I mean in this example, such that point A reach to this location, point B is gonna see the other extreme location. Now, A prime, B prime. At A prime, the shear stress is equals to 0 because there is no term in y direction. Also at the B prime, we are gonna have this shear stress equals to 0. It tells me that these 2 points are the principal normal stresses because at the principal stresses we don't have any shear. So it tells me this angle is gonna be 2 times phi p. So if you measure this angle, you will know how much you should rotate the state of stress element to get the principal normal stresses. And it's a twice of the phi p. It's a common mistake that I have seen before a student measure this and just forget to divide by 2. It's a 2 phi p, not phi p. And this is how you can find the angle of principal direction and the value for sigma prime 1 and sigma prime 2. So what would be the value of this, the coordinates of this point? From here to here, it's going to be the center, C, and from here to here, it's going to be R. So sigma prime 1 is C plus R. Whatever is the coordinates, which is sigma x plus sigma y dividing by 2 plus R. The R is over there, which is exactly same as this square root. To find this, C from here to here, if I subtract R from that, I will get sigma prime 2, C minus R, which is the first term minus the square root. So this is how you can find the sigma prime 1 and sigma prime 2. You can measure one more thing. You can measure this angle and represent that as a 2 phi p, or if you want to just show that you will get the same result as the transformation equation, we are looking for this angle. So the tangent of this angle is going to be this length divided by this guy. So the tangent of 2 phi p is this guy, which is tau xy, divided by this length. From here to here, what would be the length of this is going to be sigma y plus sigma x minus sigma y. I would like to get half of that is going to be sigma x minus sigma y divided by 2. So this length is going to be sigma x minus sigma y divided by 2. So the tangent of this angle is this length divided by this one, which is exactly same as the principal direction that we have on that table. Let's look at shear stress. If I rotate this line such that point A reach to this position, then point B is gonna be at B prime. So this A prime is gonna have the greatest shear stress. So this point and this point are gonna give me the extreme value for the shear stress. What would be the shear stress at the extreme position? It's gonna be R. What is the R? What's the R? The R is over there, which is equal to this one, positive of this square root. What is the another extreme value for the shear stress? Is going to be negative R. It's the radius of the circle. I will get negative of this value. And what would be the angle? How much should I rotate this line? This one is 90, and this one is 250. So 2 phi s is going to be 90 plus 2 phi p. As you see, I can say 2 phi s minus 2 phi p equals to 90, and phi s minus phi p equals to 45 degrees. Again, the difference between 2 phi p and 2 phi s is going to be 45 degrees. You can get the other angle as well. If you want, you can move in the opposite direction, in the clockwise direction. Point A is gonna move here, and point B is gonna be at this location. Point A prime is gonna see negative value, and point B prime is gonna see positive value. And again, we just switch the value. It's not gonna change. Make sense? And what else? All right. Let's work on one example, and then we can do a class activity. Sigma prime 1 is C plus R, sigma prime 2 is C minus R. All right. Make sure that you follow the steps and have a complete understanding about the Mohr circle. So suppose I have a plane stress with this value. Sigma x is positive 80 megapascal. Sigma y is positive 40 megapascal. And tau xy is positive 30 megapascal. When I want to draw the stress element, it's a plane stress element because there are no terms of z. I don't have any sigma z, tau xz, or tau yz. So on this plane, I have sigma x positive, so it's pointing, it's going out of the plane. Sigma y is positive, it's coming out of the plane. I said positive 30 megapascal. If I said positive 30 means on this plane, it should make counterclockwise rotation. So I know that I should put the arrow in this direction. If I tell you tau xy is negative 30 megapascal, it means on this plane it should make clockwise rotation. So you should put the arrow in the other direction. So since it's positive, I should put in this direction, and here I have to put the arrow in the to the right side to avoid the rotation, because it's gonna make the rotation in this direction. The other shear stress should make a rotation in the opposite direction. So it's sigma x, sigma y. So whatever goes up on the other side should go down. If it goes to the right, it should go to the left. We calculated the principal direction and principal normal stresses when we worked on this example. Now I would like to work with a Mohr circle. I pick one point here, point A, point B. Point A has the coordinates of positive 80. This shear stress is making counterclockwise, and the Mohr circle is negative, so negative 30. And point B is positive 40, and this is making clockwise is positive 10. One, two, three, 4, 5, 6, 7, 8, 9, 10. One, 2, 3, 4. And 20, 30. 40, 30. So let me locate the points. Point A is positive 80 and negative 30 right here. And point B is positive 40 and positive 30. 40 and 30. If I connect them, I will get this line. I will get this circle. Where is the center? Center is sigma x plus sigma y divided by 2. 80 plus 40 divided by 2 and 0, which is 60 and 0. As you see, it's passing through points 60 and 0. What is the R? Let me calculate the R right here. R is sigma x, 80 minus sigma y, which is 40 divided by 2 squared plus 30x squared. It's going to be almost 36. almost. Now, any question so far? I just looked at the circle. I could find the center and the radius of the circle. Now, if I want to find these 2 points, which are principal normal stresses, sigma prime 1 and sigma prime 2. One way is using the transformation equation, that we know how to do that. The other way is looking at the Mohr circle. What would be sigma prime 1 if you look at the right side of the board? C center plus the radius. So sigma prime 1 is C plus R, which is C 60 plus 36 is going to be 96 megapascal. So this is going to be 96. And sigma prime 2 is C minus R, which is 60 minus 36. It's going to be 24 megapascal. Yes.
Where did the 36 come from?
36 is the radius of the circle that I
Oh, okay.
calculated right here.
Thank you.
Any questions so far? All right. Now, the next question is, how much should I rotate this? It's going to be this angle, but it's going to be 2 phi, not 1 phi. You can either measure that, or as I said, the tangent of this angle, which is this length is tau xy. This length is tau xy per degree. And divided by this length. This length is going to be sigma x minus sigma y, which is going to be the entire of this length, divided by 2, it's going to give me this one, which is, if I do that, I will find we worked on this. 250 is going to be 28, one of them, 56, and 50 is going to be 28. One angle is 28. P1. P2P is going to be 180. We usually look at one of them because the other one is 90 degrees far from the first one. We will get the same result. Now, if I rotate, it tells me, if I rotate this one by the angle of 28 degrees counterclockwise, because it's a positive. If I pick a plane with 28 degree angle with the original stress element, the value of the normal stress applied here is going to be 96, and shear stress, as you see, is going to be 0. And on this plane, I will get the other one, which is 24. And shear stress is going to be 0. And you can draw the other term on the other side. To find the principal shear stresses or extreme value for the shear stress, as I said, tau extreme is going to be positive R and negative R. R is 36, or it's going to be positive and negative 36. It's a maximum value for possible for shear stress, right here and down there. What would be the angle? Again, you can, let me rotate move in the opposite direction. If I rotate this line in this direction, point A is going to be at this position and point B is going to be at this position. What would be this angle? This one is 56. 90 minus 56. 90 minus 56 is going to be 34. It's a 2 phi s. So phi s is going to be half of that. It's going to be 17. And since we're rotating in clockwise direction, I put negative 34, or yes, it's going to be negative 17. Now, if I rotate the original stress element in negative 17 degree, point A is gonna show up here, point B is gonna show up there. What would be the coordinates of point A? Point A is gonna see negative shear stress of 36, and negative means counterclockwise. So I should put the arrow upward because it's making counterclockwise rotation. What's the normal stress at this point? It just equals to the center, and center was 60, and it's positive, so it's coming out 60 and 36. And for point B is gonna be here. Shear stress is gonna be positive 36, and positive is clockwise. Clockwise is in this direction, and sigma y is gonna be the same as sigma x, because both passing through center is gonna be 60. Good. You might say, what if we rotate in this direction? So this direction, I can show you that we will get the same results. So this angle is 56 plus 90 is going to be 90 plus 56 is going to be 146. It's a 2 phi s. So phi s is going to be positive 73. So I rotate it by positive 73. So if this is the original, point B, point A, I rotate it by degree. What is the coordinates of point A? Point A right now is going to be here. Point A is going to see positive 36 as the shear stress, and positive is clockwise. So here I should make a clockwise. And normal stress is 60. Point B is going to be here. It's going to see negative 36, which makes counterclockwise, and positive 60. And just complete the other sides. Compared with this. This goes out with the 36, this goes out with the 60, and they are identical. So either you move through the clockwise or counterclockwise, you will get the same stress element. Any questions so far? I'm gonna show you how you can use the mechanical design toolbox to get this result by using the MATLAB toolbox. Alright, I'll do it once. Just make sure that you know what you need to do to use the mechanical design toolbox. All right. If you log in on your Canvas,
Can you
if
turn off the
remember I
front?
said I created modules to just organize the files.
Can you set the first little row of lights? Just so it's kind of
The lights, they're causing washout on the screen.
No, like the ceiling
The
lights.
ceiling, yeah, the ceiling lights.
Yes.
The roof.
Like the roof, just like that lights up on
Like after you switch over.
Yeah, look, it's
Thank you.
yeah.
Thank you. It's better. Thanks. I don't know how to change the resolution of my screen, but I hope you can see that. All right. We are on week 3, so you can see the 2 lectures video for yesterday and Monday. And here, mechanical design toolbox and another mechanical design toolbox. This is a zip file. It's a RAR version, but it's a I just wanted to have as a one zip file, so I created a RAR. So you can either download this, or if you go here, if you go right here, you will see many files, many M files and other files. Then you have to download all M files on your desktop. So either using the zip file, which is only one file that you can just download. In process, maybe it's still downloading because I just uploaded on the Canvas. So if this one didn't work, just go to this one and download all M files on your desktop. So I have done this here. This M file, in this folder, MDT. You can see here. I saved the all files on this folder, Mechanical Design Toolbox. When you open your MATLAB, first of all, you need to go and put this folder on the pathway of MATLAB. So I put it on the desktop. What I did, I just clicked on here, desktop, and MDT, and open. So on the left side, it brings all M files inside the M file. So these M files are applicable for different purpose. So it can use to do the Mohr circle analysis. It can be used to do the stress analysis. It can be used for mechanical components like cylinder, spring, beams, columns, many things. Fatigue analysis. So it's really good to check our calculation or our design with this one. So one of the M file that you will need to use for now is a Mohr underline tool. So I'm just typing Mohr with capital M underline tool. If I click enter a GUI, this page is gonna pop up. So it's asking you four things. Right now we are using three things. I will explain the fourth term. The first row is asking you about sigma x. What is the normal stress in x plane? So here in this example, it's positive 80. I'm just typing positive 80. Second one is asking for sigma y, which is 40. And the last one is asking for tau xy, which is positive 30. I will work on the last one, which is phi, later, but after you enter the number, just click the draw. So this is this line with this point, which is presenting point A. This is the original stress element that I have here. This is principal normal stresses. You cannot see the numbers, but I can see 96, this arrow, and 24 is this one, which is this guy. 96 and 24. Also, it provides the angles right here. What would be the principal direction? It's 28.15. And here you will see the X-ray value for the shear stress, which is this guy. 60 and 60 here and 36 as a shear stress. So some of the homework problem is asking you to use this toolbox and print out the results and attach to your homeworks. So make sure that you know how to do that. The last row that I asked you, I would like to talk about that is it's a phi. What if I would like to rotate this one by the specific angle, 45 degree. I would like to rotate this by 45 degree, and I would like to know what would be the normal stresses and the shear stresses on point A and B. Just enter 45 here and click draw. You will see another line, and this is the new stress element which has 45 degree which is 45 degree offset from the original one, and the value is going to show up here. Make sense? All right. So if you have any question about this, just you can ask me after the class. We are not done yet. So since you need that one for homework, I just wanted to explain that before we finish the class. Now, after you got the principal normal stresses for plane stress elements, in this case they are 24 and 96. We talked about the third one, which is 0. The third principal normal stresses, it's going to be 0. So sigma prime 1 is 96, sigma prime 2 is 24. Now rank them such that sigma 1 is greatest, sigma 2 is the middle, and the sigma 3 is the smallest bit. So when I look at sigma prime 1, sigma prime 2, and sigma prime 3, I can see that sigma prime 1 is going to have the greatest value here. Sigma prime 2 is going to have the second largest, and sigma prime 3 is going to have the shortest or the smallest value. So I can say sigma 1 equals to 96, sigma 2 equals to 24, and sigma 3 equals to 0. Now, if I ask you what would be the maximum shear stress, if you remember, the maximum shear stress is always sigma 1 minus sigma 3 divided by 2. So 96 minus 0 divided by 2 is going to be 48. Tau max is always sigma 1 minus sigma 3. As you see, 48 is the maximum shear stress, but the extreme value that we got here was 36. So you shouldn't introduce this as a maximum shear stress. You should rank them first and then calculate sigma 1 minus sigma 3 divided by 2. Then you can find the maximum value for shear stress. Alright, so on the slide there is an example that it's asking you for this given stress element, positive 80, negative 50 shear stress or 50 megapascal clockwise. As you see, if it says clockwise, you should put the arrow on this plane in this direction. If you put arrow in this direction, the other arrow's direction is gonna be determined. So the first plane is important. And it's asking you to do to find the principal stresses and principal direction with doing the Mohr circle and using this transformation equation. I'm not gonna go through this example. I'll just leave it for you. And here, it's gonna do the same thing that we did. It's gonna derive this stress element and this stress element, and it's gonna do it by using the MDT toolbox. So make sure that you download the MDT toolbox on your desktop and start working with that. I'm gonna post the first homework by tonight, which is due next Thursday.